Hey there, Physics 131. This is the extra bonus video for chapter or for class 36, in which I'm just going to go over 3 more written questions, which I had sort of been planning to do today, but I didn't quite get to it. So I'm just doing this for YouTube only. This is the showing the rubric for chapter 9 questions on rotational motion. And there's lots of different kinds. It gets a little more vague in chapter 9, 10, and 11 because there's a lot of different representations you can do. But basically, let's just do one. Imagine that our sun ran out of nuclear fuel and collapsed, which is actually going to happen in only about 5 billion years, probably. What would its radius have to be in order for its period of rotation to be the same as the first discovered pulsar, PSR B1919 plus 21, which has a period of a rotational period of 1.34 seconds. So this is a conservation of angular momentum, so conserve rotational momentum. And that's because there's going to be no external torques. So you have to draw then the initial and the final situations. So the initial is that the sun is kind of big. It has some R initial, which I would have to look up, but I can do that. I've looked it up on Wikipedia. The radius of the sun is 6.96 times 10 to the 8 meters. So it's quite large, 696 million meters or 696,000 kilometers, much bigger than the Earth. And then it has a T initial of 25 days. That's the rotational period of the sun. And then finally, if it shrinks down, it'll have some R final, which we don't know, and a T final is going to be 1.34 seconds. So the system is the sun. So assume that there's no external torques on the sun. So what that means is that L initial equals L final. So that's just how I would write that. And so I would just say, I wouldn't do any bar diagrams or anything, but basically L is equal to I times omega is rotational momentum. And the rotational momentum stays the same if there's no external, I guess, torque impulse or rotational impulse or something like that, which is certainly the case. So M is constant. And we can also, I should put it here somewhere here, is that assume, we might as well assume the sun is a solid sphere. So we'll have to look that up as well, but I got I is equal to, I think it's 2/5 mr squared. Put that little aside here. I don't think it's going to matter, but assuming that it keeps the same sort of shape as it shrinks, then what you've got is L initial equals L final. L initial is going to be I initial times omega initial is equal to, and the other thing we need to know is that omega is equal to 2 pi over period, right? I final, omega final. We are asked about period, so we can right now convert that to I initial times 2 pi over period initial is equal to I final times 2 pi over period final. We can just divide both sides by 2 pi, I guess, if we want to get rid of that. And then we can also use this equation for rotational inertia, and we end up with 2/5 of the mass times R initial squared over T initial is equal to 2/5 m times R final squared over T final. And again, we can divide both sides by a constant. There's the The mass is the same as it shrinks, is the assumption there, and 2/5 goes away. So you just end up, we can solve, kind of rearrange that, solve for, we're trying to find our final. So our final is equal to our initial times the square root of T final divided by T initial. So our final is equal to that 6.96 times 10 to the power 8 meters times the square root of 1.34 seconds divided by 25 times 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute. And I get 5.5 times 10 to the power 5 meters. So to put that into terms, if we change to kilometers, we divide by 1,000. So 5 minus 3 is 2, so it's 550 kilometers. And that's pretty small for a star. And in fact, it's about the size, maybe a little smaller, of a white dwarf star, which is what the sun will become when it shrinks down and runs out of hydrogen at the core. Okay. Chapter 10, vibrational motion. Again, kind of vague here, but you state your assumptions and represent the process. Okay, so if necessary, you might have to use these simple harmonic motion kinematics equations. You might have to use force diagrams. You might have to use work energy principles, maybe some energy bar charts. It sort of depends on the problem. But let's just do one particular problem. Let's say that you attach a 1.6 kilogram object to a spring and pull it down from equilibrium position and let it vibrate. So I think they're talking here about a vertical spring, mass hanging from a spring. Mass is equal to 1.6 kilograms. Pull it down 1.3 meters from its equilibrium position and let it vibrate. So what that means is that A equals 0.13 meters. That's amplitude of simple harmonic motion. Okay, because it's going to go again up and down around equilibrium. And then the period T is equal to 5 seconds divided by 10, 5.0 seconds divided by 10 vibrations. And it's trying to find what is the spring constant of the spring. So that's, we're just going to assume SHM, no dissipative forces. I guess we could say that the system maybe is the mass, something like that. So anyway, we just use that the period for mass in a spring is equal to 2 pi times the square root of m divided by k, and solve for k, because we have all those things, right? So 2 pi over, t over 2 pi is the square root of m over k. So just square both sides, and we get t squared is equal to 4 pi squared is equal to m over k. T squared over 4 squared equals m over k. Solve it for k. I get k is equal to 4 pi squared times m divided by t squared. So k is equal to 4 times pi squared times 1.6 kilograms divided by 0.5 seconds. Sort of did this in my head here. If it's 5 seconds to complete 10 vibrations, then the period is half a second. So squared. So I got, plugging that all into my calculator, I got k is equal to 250. I'm going to put it into SI units, newtons per meter. A strong spring. And how do you evaluate this? I don't know. You could also say as m, it goes up, stiffer spring is needed or something like that. M is on the numerator there. That kind of is another way to evaluate, sort of a limiting case. And then lastly, chapter 11 on mechanical waves. So same sort of thing. It's going to depend on what's going on in each question, what you do here in steps 2 and 3. You represent the problem using mathematical relationships. So it could be, there's a lot of different little parts, but let's just do a Doppler question today, and then I'll be done. A car horn vibrates at a frequency of 250 hertz. Determine the frequency a stationary observer hears as the car approaches her at a speed, typo there, of 25 meters per second. So the car is now moving and beeping, beep, and sending out this wave, and it's going. So it's moving at some Vs is equal to 25 meters per second towards the observer. VO is 0, it's just sitting there. F of the source is equal to 250 hertz. F of the observer is equal to question mark. That's basically it. We're assuming here that Doppler shift will cause a slight increase in the frequency. Will cause frequency to increase slightly. So instead of 250 hertz, you might hear 260 hertz or something like that. That's my kind of guess. Let's use V is equal to 340 meters per second is the wave speed of sound. And hopefully on the final assessment, I would actually give you that equation. You can use 340 if it's not there. So we're going to use equation 11.15 from Etkina, but it's for the toward version. So when it's toward, it's a little higher. So you want the denominator to be a little lower. So you're going to use the minus sign. Use minus sign in the denominator. And the way I remember to do that is that I need it to be a little bit bigger than the frequency. FO is equal to Fs times V over V. V is the speed of sound. Vs is the 25. You're going to minus it off the bottom. That way your denominator is a little less than 1 or a little bit less than V, and then you're going to get a number that's going to be a little higher. So you're going to start with the 250 hertz and times it by 340 divided by 340 minus 25. And I got 270 hertz is the observed frequency. And again, makes sense as it is a little higher. And that's it. A little higher pitch because the horn is coming towards her. Okay, that's it. And I'll just post that as being a supplementary YouTube video. Okay.